Hi guys. Today we're going to officially learn how to solve by graphing, which is also like the activity that we did in class today. So today's videos will be very quick. When we are solving a system of linear equations by graphing, it's really important that our graph is 100% accurate. And the only way that you can guarantee that is by using graph paper. So for today's notes and for tonight's homework, it is mandatory that you use graph paper. If you don't have graph paper at home, there is a website on the virtual classroom that you can click on that will be a place where you can print graph paper from your computer. It's on the bottom shelf of the bookshelf. It looks like a piece of graph paper. So make sure to, if you need to pause the video and go print that out right now, go print it out before you start taking notes. When we are solving a system of linear equations by graphing, first of all, I will always make sure that these problems have whole number answers. It's very difficult to get an accurate decimal or fraction answer from a graph. That's why we have other ways of solving, like yesterday's substitution. Also, it's very important that our lines are 100% accurate. The best way to make a completely accurate line is to use slope-intercept form. In the past, I told you don't change it, keep it in the format that it's in and graph it like this. But for this chapter, it's actually best to just convert everything into slope-intercept form. To convert a standard equation into slope-intercept form, you have at most 2 steps. It's really quick, really easy. Step 1 is to subtract your x to the other side. In our first equation, that's the only step. If there's also a number in front of your letter y, that would be step 2. Step 2 would be to divide everything individually by the number in front of y. That's not the case for this problem, so I will not be doing that on the first example. Once you have it in slope-intercept form, remember that you're going to start with your y-intercept, which is the second number. And that's where you're going to graph on the y-axis, which is going up and down. So I'm going to start at the positive 1 on the y-axis. Now, we want our line to be as straight as possible. And so I'm not going to just draw 2 dots and connect them. Even if I use a ruler, if my ruler is just like a teeny tiny bit off, then my line won't be perfect. So instead, and the reason why we're putting it in slope-intercept form, I'm going to do my slope as many times as humanly possible, given the size of my graph. My slope in this problem is -1 over 1. Notice that I only said that one of the numbers was negative. So for my slope, I'm going to rise -1 and run +1 down and to the right. And I can keep going down and right, down and right, down and right, down and right. Or I can also go in the opposite direction. So remember, we're trying to get 2 lines that intersect. We're not really sure where the second line is going to go. So we don't know if it's going to intersect down or up. And so I can keep going down and right, down and right, down and right, or I can go up and left, up and left, up and left. And so I can go both directions. And I already know the answers to this problem, so I didn't graph as many dots as I normally do, but I normally graph all the way to the edges of the graph just to be safe. Once you have a ton of dots going all the way across the graph, then you can connect them together to make a line. Next, I'm going to take my second equation and change it to slope-intercept form. Again, I'm going to subtract the x on both sides. And then I do need to do a second step, which would be dividing everything by -1. For my final slope-intercept form, I get y equals positive x plus 3. I'm also going to graph this. So I'm going to start at the plus 3 on the y-axis. So I'm going to go up to the positive 3. The slope for this problem is +1 over +1. So I'm going to go from my dot up and right. Now, when I go up and right, that's actually taking me further away from the original line that I drew. So I don't want to keep going up and right, up and right, up and right, because that's going to take me further away from where I want to be. So after doing that first dot, I'm realizing I'm going in the wrong direction. And so instead of going up and right, I can do the complete opposite, down and left. And when I go down and left that very first time, I put a dot on top of another dot. That is the goal. That's what we're trying to do. We're trying to get two dots right on top of each other because that's the point of intersection. And that's what we want to know. We want to know, where do these lines cross? So at this point in time, I don't need to draw any more dots for my second line. I am going to draw a second line so I can see my two lines. And I'm ready to write my final answer. Now, unlike last chapter where the graph was the final answer, in this chapter, as stated before, all of our answers are ordered pairs. So my final answer is going to be the ordered pair where these two lines are crossing. And these lines are crossing at -1 on the x and +2 on the y. So my final answer is -1, comma, +2. And that's it. You need to know how to graph accurately, and you're looking for where do the two lines intersect, and then write an ordered pair for your final answer. Now, as we discovered in our activity today, there are some special cases, so let's take a look at those. Again, I'm going to change both equations into slope-intercept form. For the first equation, I'm going to subtract the x from both sides, and then it's in slope-intercept form. And I'm going to graph that. It's the same one we had on the last problem. It starts with the +1 on the y. My slope is -1 over +1. And I can keep going, and I connect my dots. Now my second equation is already in slope-intercept form. I don't need to change it. I'm ready to graph it right now. For the second equation, I will be starting at the number 2 on the y-axis. For this equation, my slope is -1 over +1. So down and right, down and right, down and right, or up and left. Now, I hope at some point in time, and maybe even before you graphed your second line, you realized that these are parallel lines. I know these are parallel lines because they have the same slope. The geometry definition of parallel lines are two lines that never intersect. So no matter how many times I do my dots for my slope, these lines will never cross. Since they will never cross, this problem has no solutions. There is no point of intersection. There is no single dot that exists on both lines. Now, it's really important for the parallel lines, you do have to have the same slope. So if you have two equations that have a different slope and you graphed them and they're not crossing, that just means that you haven't drawn them far enough. So the only time that you can write no solution is if you are 100% sure, guaranteed that they are parallel by stating that the slopes are the same. Otherwise, if the lines are not connecting, you just didn't draw them far enough. So just have them keep going and they will eventually connect. Now there is another special case, so let's take a look at our last special case. Again, I'm going to solve this problem by changing it to slope-intercept form. For the first equation, it's just -x, and we have that same line that we've now drawn 3 times. On your homework tonight, if it says graph to solve, you must graph. So make sure that you are graphing 2 lines on each coordinate plane. For the second equation, to solve it, I'm going to minus the 2x on both sides. And then I'm going to divide everything that's 3 places by the number 2 that's in front of the letter y. After I've done that, I get y equals -x plus 1. Now, if I graph this line, I'm going to use the exact same dots that I used for the first line. It goes here, and there, and all the dots are the same because it's the same equation. It's the same line. Now the question is, where does the first line intersect the second line? So here's my first line. My second line got drawn right on top of the first line. It intersects everywhere on the whole entire line. One thing we talked about in class today was that a line has an infinite amount of solutions. So if I draw a line on top of another line, those are touching in an infinite amount of places. So we say infinitely many. Now, something that I want to point out is you're not allowed to write all real numbers for this problem. All real numbers means that literally every single part of the coordinate plane is an answer. That means over here is an answer, over here, over here, over here. And so we can't write all real numbers because it's not everything on the coordinate plane. It's just everywhere that the line exists. Since the line is an infinite length, we say infinitely many. This concludes the graphing portion of today's notes.